hear me? Oh. Yeah. Okay, so I'm skipping to a different subject, which is the impact of climate change and actually the interactions between climate change, between climate in general, and energy systems. And I present myself. So I'm Robert Vautard. I'm a research director at CNRS, and I work at LSC, which is a CEA, CNRS, and University of Versailles-Saint-Quentin laboratory. And I will present some results of several projects, among which an internal project and a European FP7 project, which is a part of this project, of course. And I made this with several colleagues. So I'm initially a meteorologist, and I became a climate scientist, like other colleagues, like many meteorologists, actually, because climate is a really interesting science. So my presentation plan, so I don't know much about energy, but I'm learning a lot here, and I will try to present some of things about interactions. So I will present first a counterpart which is more local or regional of what Jean-Pascal presented, which is regional climate modeling. So I will not describe many things about that, but there's a whole science behind. And explain how we can use that for evaluating the impact of climate change on wind energy production, and also other topics. And also spend some time on another topic which becomes an issue now, which is the evaluation also of the climate impacts of energy in the regional realm. So you have seen this picture. So this picture has been done with a number of global climate models with the choice we have, the choice. And then what we want to know, once we've said that, is more what are the consequences of our choices. And these consequences are at local areas, regional scales. They influence policies, they influence local weather, local catchment of water, rivers, etc., local economies. So we probably need more refined climate in order to calculate the impacts and also adaptation strategies. So this is what the regional climate modeling aims at, as taking from a global climate model which has a resolution of, say, 100 or 200 kilometers, and downscale this climate to a more specific region with a much higher resolution. So the idea is then to provide so we do not solve the equations over the whole globe, but we take boundary conditions and also a better description of the land, the orography, etc., the land use, land cover. And with this, we try to have a description of climate which has a more practical use for adaptation. And also, it's also important to understand that extreme events like precipitation, heavy precipitations, are not well described by these global models because these models describe kind of averages in boxes, and for processes which are in the tails, it's always difficult to describe them with kind of averages. So it describes extreme events, and future extreme events is going to be very important. And also to evaluate the effects of regional policies that can be land use, development, that can also be air pollution, the effect of land use, etc. And I'm going to spend some time on that. So just an example of this downscaling technique that we did in this FP7 project. was to look at, to ask ourselves what would look like, what would Europe look like in a +2 degree climate. So we have to remember that +2 degree has been agreed by the nations. Well, it's a quite more or less arbitrary number, but it's been agreed. So it's very important. So we need to know what the European climate looked like. So we did some experiments. So this is not the last IPCC report, but these are trajectories of the temperature from the stress A1b, previous climate scenarios, taking the zeros around the end of the 19th century and calculating a reference value here, which is the warming between 71 and 2000, about 0.46, and then start the different simulations. So that was the global simulations. And we end up with a 2 degree, which would be about centered between about 2025 to 2055, with an average about 2045 if we look more carefully. So the 2 degree is really in 20 to 30 years. So we want to know what it looks like. So these GCMs, global climate models, have been regionalized by what we call RCMs, regional climate models. And to give you just a very schematic pictures, and so these are statistics from 15 models. So it's interesting to see that we hope to have, with these 15 models, or if we can take more, we take more, but here in this exercise we took 15. We hope to have we hope to span the uncertainty, which is an assumption, of course. We will never verify it, or we will verify it maybe in, etc. But we have access to this uncertainty. So this is the average among these 15 models for the 2 degree period in Europe in summer and in winter. So the interesting thing is that in the summer, in any case, the Europe is warming much more actually than the 2 degree itself, especially in the south in Europe and in the north in the south in summer, sorry, and in the north in winter. This has a reason, very simple reasons, because we have feedbacks with soil moisture and droughts between heat waves and droughts in the south of Europe, and we have also feedback with the snow melt in the north of Europe and an acceleration of warming in the winter.
Can you include El Niño effects?
El Niño.
Can you include it?
Well, the El Niños are simulated by these global climate models, so they are in it, the effect, but for Europe it's small. Precipitation, all models agree on increase of precipitation in winter, and actually you see some gray zone where less than 75% of the models agree on the sign. So we don't say anything on these areas in the winter, but they do agree in the north of Europe, and they also do agree on the kind of central band, central southern band of drought in the summer and increase in precipitation in the winter in the north. So this is the typical climate change we will get. So we can look at other indices like extremes. For instance, the 20-year return time, I remember it, but the 20-year return time of heat waves, of extreme temperature, should be increased kind of homogeneously by 2 or 3 degrees, which means that in a 2-degree world, if you get something like 39 degrees in Paris, you would get 41 or 42 degrees, if I remember correctly. Okay, now, so there has been a number of exercises of regional downscaling. It's going on at the moment. There's an international experiment with all the models and different regions. I'm not going to describe this. It's called CORDEX, Coordinated Downscaling Experiments. And we get results. So this is typical from this Euro Cordex. We have several runs for Europe. And here, actually, it's for an area, an average of summer temperature around Paris. And we also plotted the observations here in black. You cannot see them. So, of course, the observations don't match with the models. We don't expect that because these are not, these are actually CO2 years. These simulations have been initialized well before. So we don't expect them to match. What we expect is the statistics to match over this period. So you have here the summer of 2003. And it's interesting to see that in some scenario with climate policies, this blue one, it's one of them. And in this blue one, we get some 2003 types of events in the end of the century. They're slightly higher. But in the business as usual, the 8.5, it's quite interesting to see that in some scenarios, the 2003 heat waves is becoming a cold spell in the end of the century. And actually, the heat waves, some of these models provide a heat waves with anomalies of temperature of 9 degrees. 2003 was 3 degrees. So you can imagine 2003 with 6 more degrees. So that's quite a lot. And also what's interesting is that you can follow the red curve here. It can be, you can have no heat wave for 20 years. And then suddenly one, which is 3 degrees more than 2003. So that's very important. Are we prepared for that? Not sure.
Winters, which are at the level of the summer of 2003.
Sorry? No, that's summers.
This is only summers.
Summers.
Not the inner cycle.
No. In this red one, which is a Swedish simulation, in this red one, the 2003 event becomes a cold event, a cold summer. Okay, so that's the typical thing. Now, what can we do for energy? So there are impacts for energy. There's a lot of things going on, there are a lot of studies. There is a risk of lack of cooling water, for instance, for nuclear power plants. There's a very nice study published in Nature Climate Change from a Dutch team. And the energy demand will be modified. Its variability also will be modified, so it's very important. There are risks of power outage which are changed. It needs to be studied. So these are the peaks kind of type of event. And there are changes, important or potentially important changes in renewable energy resources, water resources, wind, solar, etc. And I will focus on wind, because wind is my preferred topic, but it may not be the most important, although I will talk about that now. And yes, so there are other applications of regional climate modeling. I don't want to talk about it because I don't have time. So for the moment, I will talk about the impact of climate change on wind power potential and production. So what do? We take the same 15 models, 15 simulations, but instead of looking at temperature, we look at wind. And we try to see if the wind will increase or decrease regionally, and if it will help wind energy or if it will not help wind energy. But here we have to have what we call an impact model. So it's a chain of processes that start from the global model, regional model, and then extract the wind, do some assumption for having the wind at the turbine height. Actually, we can have from the models the wind at the turbine height, but it's not a standard output. So from these 15 models. So we don't want our colleagues to redo their simulations, and we just fit some statistical model for that. And then we can calculate at each grid point a power curve applied to the wind and calculate the wind production or the potential wind production. And finally, I will show some other examples. So here is a map based on an average. It's not really nice as I see it. It was nicer on the computer, but it's 2050 minus present. It is the change in the potential wind production. I think the title is wrong. It's potential production, meaning that if you put one wind turbine in each grid cell, this is the relative change of production you obtain between 2050 and now.
In percent?
In percent. It's very small on average. It's quite small. There is some, so the areas where I put the dots here are actually the areas where more than 75% of the models agree on the sign. So there are areas where really we don't know. There is a tendency to increase around the Baltic Sea and Baltic area, so it's good for German and Swedish, and it's bad for Italian and Spanish. Okay? So typically, this is what we obtain. The nice thing with this, and I think this is the first time we could show that, is that we have 15 models here agreeing on the sign. So it's not, it becomes more credible if we have so many models agreeing than just one model. So this is very important. Now, if we do impact studies, we never can conclude anything about the results of one model. Now, the interesting thing also is that here is a map of all the wind farms actually that are in Europe. So there's a lot in Germany and Spain, Italy, southern Italy, etc. And in 2012, and we can calculate actually the national productions. And I'm skipping a little bit. We can calculate the national production by aggregating. And now I skip to the scenario. So what we did here was to take the climate and energy package and try to apply this to the scenario of 2020. We didn't have the 2050 at the time of the study, and I don't think there is an agreement on the 2050 scenario, at least in this, at this European level. And these are numbers for each country, which are onshore, offshore, 2012, and projected or committed for 2020. So there are countries which are close to commitment, to achieving commitment, like Germany, at least for onshore. Offshore, it needs some expansion, but France is very far, and other countries are very far also. So we could take this energy package, and now the problem we have is where do we put the wind farms? So there are ongoing projects, but there are also commitments of countries where we don't know where to put the wind farms, actually. So the first step was to spatialize the scenarios. So here it was done in a very crude way by looking at wind resource and filling grid cells which have a higher wind with aeolian farms. So that's a bit stupid, but because we get a lot of wind farms over the mountains, for instance, because there's a lot of wind on the mountains. So even so, it's an example of the methodology. Now we have a tool to spatialize the scenarios, which takes into account different constraints, and also the fact that you don't want to put wind farms in cities in particular. But actually, this is more to be taken on the qualitative level. So applying this scenario, we could calculate. So it's a 2020 scenario together with a 2050 climate. It's a bit awkward, but that's the best we could do at the moment. So if we look at the European scale, no change, only maybe 1% or whatever. So we can be reassured that the climate change will not threaten the wind energy. So at the European scale. Now, if we look at country scale, this blue is for 2050, and this blue is for 2100, or the end of the century, rather. So Italy has some. Yes.
When you say no change, it's only accounting for climate change
Yes.
on a given installed power,
Yes.
and it's between 2020 and 2050.
Yes, it's not the installed power, it's the calculated power, it's the model power.
The power change does not account for a change in the installed power.
It does not, no. It's the 2020 scenario
Yes.
that you apply today and in 2050. It's a bit strange, but... okay, so we see again that the countries like Italy, Portugal, Spain have some problems, but still we have to remind that these numbers are small and it varies between 0 and maybe minus 10 or minus 15%. So some may find important because in terms of economics it may be significant, but we also have to realize that the power, the installed power will grow in a much higher rate than that. Yes.
Just a precision, PT means after
Portugal.
And what's the
Yeah.
difference between the light blue and the dark blue?
2050 or and the end of the century. 2021, the last 30 years. The last 30 years. It's not 2100, it's 2085. It's the last 30 years, an average over the last 30 years. So, actually, this shows that the changes should not be a major threat. But we have to remember that this is only scenario A1B, so we have to redo this for the RCPs, 8.5, etc. There is definitely a need of an economic analysis also. So this is the same thing. And also, very important, we need certainly further downscaling for better resolving coastal and orography effects. These models do not solve the sea breezes and stuff like this. So that's the first conclusion. I'm not finished. How much time do I have left?
Oh, you still have 20 minutes.
Oh, that's wonderful. Now, I would like to, it's kind of strange, but these models do not really simulate one phenomenon that has been observed for several years now, and there are many papers also, which is what we call the wind stilling. So what is it? For a few decades, what we have observed is a small decline, but gradual decline of wind, especially over the northern hemisphere and only over land. So this is something, so we have time series and we have maps of the trend. So we are talking about a small trend. It's 10% in 3 decades. So it's about 10% in 3 decades. So it's not much, but still it is of some concern. Actually, we do not know where this comes from. There are assumptions, but we do not know.
It's the wind at which altitude?
10 meter.
10 meters.
Yeah, so it's very important because we do not know the causes. We have some ideas, but they are not proven, and we do not know the consequences. For instance, for the causes, climate change could be a cause. Actually, it's probably rejected as a cause of this because, first of all, the models do not simulate that. And also, there is no reason to believe that there is a kind of generalized decline of wind over land due to climate change. So one other assumption, so it could be observations also, that the wind, the COP anemometers would not work with the same quality over time, but they've been replaced. And also, one assumption is probably the change in the land use, and especially all these points are stations. Most of them are in airports, so there could have been a building popping up around the stations. We don't know. We don't have enough metadata for that. But there's a lot of papers about this. And another, I'm just finishing, another possible cause is the growth of forests. And the growth of forests. We have some indications and some measures of this carbon uptake from forest and also afforestation programs and also the abandonment of croplands, for instance, in Russia. In all these areas, we have abandonment of croplands, which makes the surface more rough. So the increase of roughness could be one of the causes. So it's not clear at all what the causes are, and it's also not clear what the consequences are. If this is a question of roughness near the ground, it's not clear whether it will impact wind energy at upper levels. We have to look for that. Sorry. Yes?
Is it observed in the
Yeah.
northern hemisphere only because you have measurements there or not?
Yeah, long-term measurements.
We have no measurements in the
Yes, there are measurements, for instance, in Australia.
Yes.
They are a bit contradictory. The measurements actually in the early years in Australia, they measured at 2 meters. So it's not exactly the same. So at 2 meters, you observe the same thing, but at 10 meters, you tend to have an increase, but at the same time, there are breaks in the time series because Australia has changed its instruments over time, and it makes the series very difficult to interpret. So that's why we prefer not to put nothing. But in Africa, we definitely have a lack of measurements. We have some measurements in Argentina trying to also a little bit of decrease. Yeah, so this is something we need to explain also, and there's still ongoing research. Now, moving to another subject, the landscape is changing, not everywhere, of course, but it's changing in many areas, and we are using bioenergy, and we are using wind farms and solar plants. And the issue is whether this has some impacts on regional climate. So this has been since 10 years an emerging topic, and we do not have a holistic view, a fully comprehensive view of this. But I want to show you the result of one of the analysis we did. So I will be looking at wind energy and trying to answer whether the deployment of wind energy in Europe will change the climate of Europe. This may seem a strange question, but there has been studies on that, and we need to fix this issue more or less. So why should wind turbines modify the energy, the climate of Europe? If we take the process, so the wind turbine takes the energy from the flow, kinetic energy, and provides power, electrical power, turbulence in the wake, and there are some remaining flow. Of course, it doesn't stop the flow. So this has nothing, we hope this will not change much the regional climate. This will put some heat, of course, because we are going to use this power. The flow remaining, and the turbulence may change. And there are coefficients measuring the dissipated part of energy to the flow kinetic energy. It's called the thrust coefficient, and the power coefficient is Cp. And there is a theory, I don't want to describe in detail. Basically, there's a theory saying that depending on the turbine and the turbine characteristic, the maximum you can obtain of efficiency is about 0.6. It's a bit slow. And we have typically this kind of curves as a function of wind speed. So Cp is typically maximal here for this turbine in the middle of the power curve, and also the thrust is decreasing and maximal at the beginning. So, okay, so there has been observations of changes in the temperatures near the ground in Texas due to windmills. So these are actually differences between temperatures over 3 years, 29 to 2011, minus 23 to 25, over Texas area. I don't know exactly where it is, but it has been shown to increase the wind farms that took place actually gave rise to some increase in temperature, which can be 0.5 to 1 degree in the vicinity of wind farms. So why is that? It's basically essentially due to the mixing of the air in nighttime, because in nighttime, usually, as there is no sun, the Earth radiates and cools the atmosphere near the ground, and the layers of atmosphere flow on top of each other without turbulence. So it helps cooling more. And now if the thing is mixed up by the turbines, then you increase the temperature near the ground in this case. So it's essentially a nighttime effect, and it can have some impacts on agriculture or whatever. It's not clear at this time, but we do measure these effects. Also, now we are going a bit more in the science fiction world. There has been some studies trying to see what would do a massive deployment of wind energy, which would satisfy 10% of global energy demand in 2100, I think. There was a scenario. And they had to spatialize the scenario, and they assumed a bit, they had to make an assumption. They assumed that they put the wind farms over areas where, which are not very well occupied, like shrubland and grasslands, and they spread it over the world and in some coastal areas as well. And from these scenarios, they could obtain a temperature change here, map. So it's a quite intensive scenario actually at the global scale. They used coupled model. They ran it for 100 years or so, and they could see some changes in the temperature, cooling there, warming there. But the important thing is that on a global average, they could not see a very significant change. So there is a kind of redistribution of the temperature and the energy at the surface, but there is no global change. There is a change in precipitation as well. Now, this is not a really realistic scenario. So what we want to do here is to use a realistic scenario. So we use the same as before, the climate and energy package for 2020. And what we did was simulations over 30 years, with and without the wind farms. And we calculated the differences between the two simulations. So we used the model, the WRF model, which was in where there is a parameterization of the turbine effects. So you can calculate at the same time the weather, the climate, and the output, the power output. So that's a nice way to have the two together. And we are trying to develop that. So first we had to evaluate the model. So we evaluated the winds. So the winds are a bit overestimated, but this is the electrical output by country, because only the electrical output are only available at country level for some countries. So this is France, Denmark, Germany, Ireland. We have some other countries as well. And what we see in general is that the model is overestimating. So this is model observations from power at the national level. So we have some overestimation. We don't fully understand why. We don't fully understand why the model overestimates, because even the overestimation of wind could not explain that. And probably there are some under-functioning wind farms, some wind farms which are in maintenance also. But we could simulate all over the years the fluctuation quite nicely These are observations in red, and in blue the model. Actually, when I showed that to RTE, they said, well, this is not good because we need 2% difference. I said, So, because of course, in a network, electric network, the demand and the production must be really balanced. So they need to have really high accuracy of prediction, of simulation. In any case, so for this scenario, we calculated the differences between the with turbine minus the without turbines. And we see these patterns for winter and for summer. So basically for summer, we could see some differences here near the coast in offshore wind farms. And, but the rest is not really significant. We show only significant areas where we have dots. And some warming here, some cooling in the southeast Europe, and, but the differences were very small. It's like 0.2 degrees, 0.2 to 0.3 degrees at most. So the conclusion for the moment was that the effect is small. However, if we look at the flow itself, well, if we look at here sea level pressure, so this is the sea level pressure difference, what we see is that the wind farms actually create an anticyclone over Europe, a small, very small anticyclone because it's 0.5 hectopascal. So it deflects, so this is really exaggerated. It's really a small deflection, but it creates some anticyclone which has some impacts, okay, on wind and on precipitation. So the question is, should we worry? Because,
Sorry.
yes,
Go back to the previous.
yes,
So it lowers a little bit the winter precipitations in Europe, right?
right, in Central Europe, yeah. That's the effect. Because you have this anticyclone, there's less rain.
What is the unit?
Millimeter per day, I think, yeah. And here it's wind is meter per second. So it's really small. But however, so this is a difference between, this is about 5%. It's not negligible. It's not negligible, but it's small. So we have to be careful. So this could, this is between 0 and 200 gigabytes. 200 sorry, I'm tired. 200 gigawatts. I think the 2020 is 200 gigawatts. I'm talking to the specialist, 200 gigawatts, I guess so. It was 100 in 2012, it's 200 in 2020. So in 2050, it could quadruple or be multiplied by 5 to 6. There are some scenarios also. So the response is certainly not linear, but the range of response should not exceed at least the interannual variability between 2 years and also the effect of climate change itself. But still, we have to study that. So the answer to this question is we should not worry, but study, of course. Because this is... Okay, there is another thing we have to say about this. This has nothing to do with the climate change due to extraction of fossil fuels. Because here we are not putting more energy in the system. We're just changing the distribution of energy. So it does not have a kind of the same kind of global effect that the fossil fuel energy could have. So this should be, the message is very tricky. There are other issues about this, the extractability of the resource. I'm skipping to this one just to spend just 1 or 2 minutes to explain that. In these experiments, these authors have been trying to see what we could really extract from wind power as a function of the expected wind power, which is the simulation where we take the wind and calculate the power from the wind without considering the interactions. But the interactions, especially in the large wind farms, the windmills are interacting with each other and degrade the efficiency. And in compiling different studies, actually from different papers, they would end up here in this diagram that there tends to be a limit around 1 watt per meter square. That is to say, you cannot extract more than 1 watt per meter square of energy, whatever the size of the farm. Or so there's a kind of wall at 1 watt per meter square. You can put bigger turbines, you can put larger wind farms, or spread more, less, etc. You'll hit this limit. So that's what we are trying to do now. I'm just going to conclude that what we are trying to do is to have a system which would evaluate the energy mix scenarios, not only wind, but we are working on solar, which is a climate model where we put in all these energy systems and trying to have the production demand. The demand is different, coming from different models, but also the climate effects and the energy outputs, etc. So weak threats from interactions between climate and wind energy from near-term scenarios. But this is an emerging topic, and there is definitely a need to do more studies on that, to better constrain models. We are lacking observations, etc., etc. Thank you.
Thank you.